Hello, today we're going to be talking about the basics of the periodic table. So the first thing that you have to be aware of is that each box on the periodic table represents one element. On each square of the periodic table, the top number is going to represent the atomic number, which if you watched my last notes PowerPoint about atoms, you'll know that already. So this number that I just circled is going to be the atomic number or your number of protons. Down below that, you're going to have the atomic symbol or the element symbol. In this case, we're talking about carbon here, so its symbol is C. Then down at the bottom, you're going to have something called an atomic mass or a mass number. Now, this number is the total mass of your atom or your number of protons plus your number of neutrons. Now, remember that these on the periodic table are an average. They're an average atomic mass, so they're not always going to be that super clean number. So if you're going to do any calculations with these, you're going to need to round to the nearest whole number. Okay. So next, I want to talk a little bit about the setup of the table itself. So your columns up and down are going to be called groups, and there are 18 different groups. You can see them numbered along the top here. So for instance, this entire thing, if I can circle it well enough, that is group 1. So everything in this column is representative of group 1. Likewise, everything in this column right here would be representative of group 2. The other thing you have to be aware of when looking at the periodic table as a whole are the periods. Period, periodic, shocking. But that's going to be each row horizontally. So period number 1 is actually just going to include those two elements, hydrogen and helium. Group 2 is going to include, period 2 is going to include a few more, et cetera, et cetera. Now, there's a lot more that the periodic table can tell us besides just what's in a column versus what's in a row. So groups number 1, 2, and 13 through 18. So that's everything that you see in white down here are called representative elements or representative elements. And they are called that because their group number means that they're going to have a certain number of electrons when ionized and a certain set of properties based on their group number. Everything that you see in yellow down here, these middle ones and the two periods down here that aren't part of the main part of the periodic table, those are referred to as transition elements because they can have different numbers of electrons when those atoms are ionized, and their properties can be slightly different accordingly. In the periodic table, as elements, you can either classify an element as a metal, a non-metal, or a metalloid. Everything to the left of this thing called a staircase is going to be a metal, except for hydrogen. Hydrogen is the one exception to that rule. Everything to the right of the staircase is going to be a non-metal, and everything that hugs the staircase is going to be a metalloid, which metalloids basically have properties of both metals and non-metals at the same time. So they're kind of walking the line between metals and non-metals. So to take a look at what I mean by staircase, this thing right here, this line that's in bold that I am doing a very poor job tracing, is the staircase. So every element that you see here in green is going to be a metalloid. Every element that's to the right of the staircase that you see in blue is a nonmetal, even hydrogen over here. I know it's all the way on the left, but it is a nonmetal. And then everything to the left in yellow, again, except for hydrogen, is going to be a metal. So if you're just looking at the periodic table, it is mostly metals. So some properties to be aware of with metals: they are generally shiny, or lustrous is another word we could use to describe them. They are generally going to be solid at room temperature, so you would hold them in your hand and they're not going to melt, the vast majority of them, except for mercury with the atomic symbol Hg. Mercury, if you've ever seen it in person, is a liquid at room temperature, but that's rare for a metal. Metals are going to be malleable and ductile. So what that means is, to be malleable, it means that if I were to take a hammer to it, it would eventually get pressed flat into a sheet. And to be ductile means that if I were to apply enough heat and try and draw that metal out, it's not going to break, it's going to be able to be drawn into a wire. You've all seen copper wiring before. That's a property of metals, and they all have it to varying degrees. Metals are also going to be a very good conductor of electricity and heat. Metals, if you've ever made the mistake of sticking something metal into a wall socket, you got shocked. That's because metals are conductors. If you've ever held a metal spoon and were trying to stir something in a pot, you probably burned yourself or came close to it, because metals are good conductors of heat as well. So here's some basic examples of metals. We have copper here. This is copper piping. We have magnesium, and then titanium over here. Nonmetals, on the other hand, now remember, that's everything to the right of the staircase. They are generally either gases or brittle solids at room temperature. Again, there's one exception. Bromine is going to be a liquid at room temperature. There's not a lot of elements that at room temperature tend to be in liquid form. Mercury is one, bromine is the other. Nonmetals are effectively the opposite of metals in a lot of different ways. They are poor conductors of heat and electricity. So that's why when you're handling electricity or electrical wiring, you want to wear rubber gloves, you want to ground yourself, and things like that. But they are also generally dull and not shiny. So that's another way that they are essentially the opposite of metals in their properties. So here's some examples of nonmetals. We have sulfur, which smells very, very strongly if you've ever been around it. We have iodine here, which, looking at iodine, you're seeing this purple smoke happening, but iodine itself tends not to be a bright purple. Iodine it kind of has this orangey yellow look to it. And then we have argon, which is one of the gases, but if you pump enough electricity through it, it will light up a certain color, in this case blue. So once again, just taking a look at those metalloids: silicon, arsenic, germanium, tin, tellurium, all of those would be qualified as metalloids, and they have properties of both. Like if you look at silicon in its elemental form, silicon can be shiny, but it doesn't, it acts differently than metals or non-metals generally do. So moving on to specific group names, there are a few groups that you do have to know. So group 1, which you see on the right highlighted in green, that group is called alkali metals. Alkali metals are highly reactive metals, but they're also pretty soft. So you've probably seen YouTube videos of this, or if you were a freshman of mine last year, then you would have seen the video of this experiment when I did it in class. but they're soft. So like sodium, lithium, you can cut them with a knife, but if you drop them in water, they explode, which is a weird thing to think about. You don't usually think of things being dropped in water and being explosive. Water is generally something that puts out fires, but not always. It depends on the element's properties. So if you're curious about that, I highly recommend you look up sodium metal exploding or any one of the alkali metals. As you move down towards the bottom left corner of the periodic table, their reactivity actually gets higher. So sodium is an explosion that you can be around, but if you try to do the same thing with rubidium, you'd have to be many paces away. Otherwise, you would get pelted with shrapnel, effectively, as whatever container that metal was in exploded as well. So those elements are usually going to exist in compound form. Like I said, their elemental form is reactive, so generally reacting will happen if it's just sitting around, and the compounds, the less reactive compounds, will tend to form. Group 2, which is right beside group 1, but it's not highlighted, they're known as the alkaline earth metals. They're also fairly reactive, but not like the alkali metals are. Like magnesium, you can touch with your hands and it's not gonna react with the water that happens to be on your skin and burn you or anything. But if you do combust it, it forms magnesium oxide, and that reaction is very, very bright. It releases a lot of heat and a lot of energy during that combustion process. So again, reactive, not as much as the alkali metals though. Your non-metals groups that you need to know, group 16 are going to be referred to as your chalcogens, group 17 are your halogens, and group 18 are noble gases. So chalcogens don't really have any properties that I need you to know, but halogens you do need to be aware are pretty highly reactive as well, though not necessarily as spectacularly as the alkali metals are reactive. Group 18 are non-reactive. They already have a full shell of something called valence electrons, which I'll talk about. So they don't tend to do anything. If you tried to react them, they might if you mess with the pressure around the reaction or put enough energy into it. But again, they don't tend to react on their own spontaneously. Because their electron shells are full, and having a full electron shell kind of controls the reactivity of certain elements. So to show you what I mean by group 17 and 18, 17, the halogen group, you can see in yellow over here. 18, the noble gases group, is going to be in red. And then group 16, the chalcogens, is right next to the halogen group. These guys down on the bottom that you can see in orange down here, they are referred to as the inner transition metals. So within the transition elements are the lanthanide group and the actinide group. And if you guys see this blank spot down here where it looks like somebody forgot to draw lines, really all of those elements in this giant orange period right here and here, all of those, their properties kind of fit right in here. So imagine that these entire 2 rows got smushed and shoved up in that space on the periodic table. That's where they would go. Just to give you some ideas about the uses of different elements, we have sodium, which is a component of table salt. Lithium is used in batteries. Calcium is important for your own personal health and your bones. Magnesium is going to be in a lot of electronic devices, including cell phones, things like that. Oxygen is approximately 65% of our body mass, which I know it seems weird. It's a gas, but oxygen is in a lot of compounds in our bodies. Fluorine, you've probably heard of fluorine referred to as fluoride. So that's going to be used to prevent tooth decay. Neon is found in neon signs. Silicon is going to be used in a lot of prosthetics, and titanium is used in frames for eyeglasses quite a bit. So that's just a few of the uses for different elements in the body. Okay, so the next thing I want to talk about with you is periodic trends. So not only can the periodic table tell us a bunch of information just by looking at an element's placement or group number or period number or anything like that, but also there's certain trends as you move along the periodic table that you're responsible for knowing. The first one is atomic radius. An atomic radius is really how big an atom is across. That's what I'm talking about when I say atomic radius. It's how big. So atomic radius is going to decrease as you move from the left side of the periodic table towards the right. And the reason for that is as you move from left to right, atoms have more of those things called valence electrons or outer electrons, which have negative charges. And since the nucleus is positively charged due to all those protons, the more negatives there are, the closer they're going to get pulled in towards the nucleus, making the distance across an atom smaller the more valence electrons you have. It is going to increase, so the radius gets bigger as you move down a group. So as you get towards the bottom of the periodic table, atomic radius gets bigger. And that's mainly because there's more protons and neutrons and electrons as you move down and get to the heavier elements. So you're going to have a larger atom, which makes sense. So here's a nice graphic that shows you atomic radius. Your biggest atoms are down here on the left. Your smallest atoms are going to be up. Hydrogen is pretty tiny. Fluorine is actually the smallest atom. The only atoms or elements that kind of don't agree with these trends as I'm trying to show them to you are really the noble gases. So if you're trying to predict how big or small noble gases are, they don't fit the trends, but all the other elements tend to. Another trend on the periodic table that's kind of the opposite of atomic radius in terms of where it gets bigger or smaller is ionization energy. And that is the energy that's required to remove one of those outer electrons. Now, again, I know we haven't talked about valence electrons a whole lot yet, but every time one of those outer electrons gets removed, an amount of energy is required to do that. Now, if you're a different atom, you could have a different amount of energy that's required to remove that outermost electron, and that's partially because of how big or small that atom is. So if an atom is really big, it's probably not going to take a lot of energy to remove that outermost electron, versus when an atom is really small, it takes a lot of energy to remove that outermost electron. So the trend is thus ionization energy increases as you move up the periodic table or as you move over towards the right. Okay, there's another trend called electronegativity, which is very similar to ionization energy, and we'll talk about that. I'm not going to cover it right now, but electronegativity also is going to increase as you move up the periodic table and increase as you move towards the right on the periodic table. So that's going to conclude my notes for you today. So make sure that you're filling out that note sheet and that you submit it on Canvas for me.